Let's talk about apparent weight. Now, as you know, the weight of an object is the force of gravity acting upon that object, which is the product of the mass multiplied by the acceleration due to gravity. Let's draw a free body diagram for this object at rest on a scale. The scale tells us it weighs 50 newtons. So we have the upward force of the scale onto the object, identified as force normal. We have the downward force of the earth on the object, labeled as mass times the acceleration due to gravity, which is the weight, which is the force of gravity. Let us sum the forces vertically in this scenario, acknowledging that the object is not accelerating vertically. The right side becomes 0, and for that reason, we can rearrange this, solving for force normal, showing that force normal is equal in magnitude and opposite in direction to the force of gravity, or the weight. So why are we doing this? Well, we're doing this to talk about what we feel as weight. Now, the weight of this object is 50 newtons. Its mass is 5 kilograms. Apparent weight is the feeling of weight. And it's due to the upward force of a surface onto an object. So what we perceive as weight is actually force normal acting on our body. And we're going to talk about this in some situations in which the object is accelerating. Okay, so if an object accelerates, the apparent weight changes. Remember, the apparent weight, what we feel as the weight, in other words, that upward contact force, force normal, is changing. It can increase and decrease depending on the direction of the acceleration. Here is an elevator. I love these problems. And in this elevator is a scale. And on this scale is a 5 kilogram object, and the weight is displayed at 50 newtons. This elevator is currently at rest. Its velocity is equal to 0 meters per second. We call this equilibrium. Now, the other state of equilibrium we've discussed in class already is a constant, unchanging velocity. So equilibrium is defined as a situation in which an object is either at rest or moving at a constant speed. In other words, the object is not accelerating. So this object is in equilibrium here. At equilibrium, the apparent weight is equal to the force normal. And we show that, and you see the free body diagram. We've looked at that many times now. So let's look at a situation in which this elevator is accelerating. Notice the length of the vector on the free body diagram is now greater for force normal than it was for the object when it was in equilibrium. When the acceleration is positive, force normal will be greater than the force of gravity. Okay? Now the weight doesn't change, but apparent weight, again, is that upward force onto the object, force normal. That does change, and I'm going to show you here why. So, if acceleration is in the opposite direction of the acceleration due to gravity, in other words, this is accelerating upward, we get a weight, as you can see on the scale, that is greater than 50 newtons, and we can actually calculate this. Force normal is going to increase, and the object feels heavier. Okay, so I can relate to this in real life from my experiences, not only on an elevator, but also on roller coasters and different rides where you feel heavier at a bottom of a loop-de-loop, which we'll talk about in another unit. Or if you're on acrophobia at Six Flags and you're falling, you feel much lighter as you're falling. This object's moving upward. we'll sum the forces vertically, where we call in our our coordinate system, we'll call up positive, we'll call down negative. So in this case here, I've subtracted the force of gravity from force normal and set that equal to mass times the vertical acceleration. Notice the right side of the expression does not become zero. This is not an equilibrium. This is accelerating upward. So we can solve for force normal by adding the force of gravity to both sides, as I've done here. Now, the key to these apparent weight problems is you are solving for force normal to find apparent weight. I can't stress that enough. In this instance here, it becomes more intuitive if you're able to factor out the mass. That leaves us with the expression, when we factor out mass, that we are adding this acceleration of the elevator to the acceleration due to gravity. So we're adding a number to the number 10, basically 10 meters per second being the magnitude of the acceleration due to gravity. And we're adding this additional acceleration. So of course, force normal is going to be greater than it normally is during equilibrium. Of course, we're showing that mathematically right here. So the weight is 50 newtons, but the apparent weight is more than 50 newtons. Please make sure you've written this down. We'll talk about this a number of times. Now, look at the vector for force normal in this scenario. It's gotten smaller. In this case here, we're going to have an elevator accelerating downwards. So it's going down. And in this case here, force normal will decrease. When the acceleration is in the same direction as the acceleration due to gravity, force normal will decrease. Again, weight stays the same, but the apparent weight, our feeling, anthropomorphically speaking, the object's feeling of weight will go down. And this also not only applies to force normal, but it applies to a force of tension, which I'll talk to you about in upcoming videos. Let us sum the forces here. Now, we've defined our coordinate system as up being positive and down being negative. We have subtracted the force of gravity, which is downward, from force normal, which is upward. On the right side of the equation, I have included a negative sign for the acceleration of the elevator. When we solve this and factor out mass, as I've implored you to do because it makes this relationship very evident, we see now that we are actually subtracting a number from 10. We're subtracting the acceleration from little g, which is 10 meters per second squared. So of course we're going to get a smaller value when we solve for force normal. We're no longer multiplying mass times the acceleration due to gravity. We're multiplying mass times a smaller acceleration value because we're subtracting that acceleration out. So the weight is 50 newtons. The apparent weight is less than 50 newtons. If you've ever been on a roller coaster ride where you're accelerating downward, you feel lighter. When you jump out of a plane, you feel weightlessness. We know these things. It's physics. This is intuitive from our everyday life, and this applies to this scenario and the concept of apparent weight. Now we have two boxes that are stacked in an elevator accelerating downward. So we're given a value. This downward acceleration is 2 meters per second per second. You are asked, what is the upward force exerted by box 1 onto box 2? By box 1 onto box 2, right here is what you're asked about. Let's go ahead and start by making a prediction. The acceleration is downward. It's in the same direction as little g. Therefore, I should get a value for force normal that is less than the force of gravity. And again, we're looking at box 2 as our object. Let's go ahead and do our free body diagram for this object, box 2. Upward force of box 1 onto box 2 is force normal. The downward force of the Earth on box 2 is the force of gravity. Now look at the length of the arrow. Okay, I've shown it to be smaller than the magnitude of the force of gravity. Okay, now let's sum the forces. Let's call up positive, let's call down negative, in which case our acceleration for the elevator is in the negative direction, and thus I've included the negative signage here. Let's solve for force normal, because that is the upward force. That's this apparent weight concept. Let's go ahead and factor out mass as we did in the previous two examples. So we've factored out the mass of box 2, which is 7 kilograms. Look, guys, we're subtracting 2 meters per second from 10. That's going to give us a value there of 8 meters per second squared. And we're multiplying that by the mass to solve for force normal, which is the upward force of box 1 onto box 2. And we get a number less than what it would normally be when it's in equilibrium. When this object, box 2, is in equilibrium, force normal is equal to the force of gravity, which would be 7 kilograms multiplied by 10. So normally this object's weight, apparent weight, would be 70 newtons. In this instance here, it is less than 70. Why? Because it is accelerating. Okay, so force normal, which is the apparent weight, is 56 newtons for this example here. Again, the weight is 70 newtons. That would be equal to force normal if it were moving at a constant speed or at rest, but it is not. It is accelerating. Its apparent weight is less than the force of gravity in this example here. I want to talk again about Newton's third law, another great application. So let's look at the force of box 1 onto box 2 is equal in magnitude, opposite in direction to the force of box 2 onto box 1. Well, box 2 is exerting a downward force onto box 1. And that downward force would be equal to negative 56 newtons. So box 1 exerts upward of 56 newtons as we've calculated. Hey, this is a force pair. This is a mutual pair. Therefore, the forces exerted are equal in magnitude. So this question could have said, what is the downward force of box 2 onto box 1? And that would be the same magnitude, opposite direction. And the last thing I want to look at here is, what if this question was asking you about the upward force of the elevator onto box 1? This is similar to the physics biotech table example I did in a previous video, where we could actually define our system to be comprised of box 1 and box 2, and we could easily solve this problem, whether it was in equilibrium or accelerating, by simply defining this two-object system and solving for force normal on our defined system. In this example and in this video, I've talked to you about the concept of apparent weight, the feeling of weight. Remember, an object's weight doesn't change, but the apparent weight can increase or decrease depending on whether the object is accelerating up or down. We are solving for that contact force. That's what we feel. And we call this force normal. So remember, guys, when doing these problems, you are solving for force normal to find the apparent weight. I'll see you guys in class.